Yeah. Now, what is a 4-bit ripple carry adder? So basically, the output of 1 would be fed as the Cin of the next full adder. We are using 4 full adders over here, okay? So this is the schematic diagram. Just understand. See, for the first full adder, A and B are your inputs. Cin is one of your inputs. So for any full adder, you would be having 3 inputs, A, B, Cin. Then C out would be, sum would be there and C out would be there. This is the sum and carry out. Next, for this full adder, we are getting the carry out from the previous full adder, and that forms the Cin for this full adder. Then similarly, you would be having another 2 inputs, B1 and A1, then S1, C out. So you would be having S0, S1, S2 and S3, 4-bit sum output, and 4-bit the last carry out would be your last carry out would be there at the last. But then what I want you all to understand is, what does this code do? Now, for example, if I ask you to write this code, right, how would you write it? Just give it a try. Let's see. You have to write a code for this circuit. How would you write? So basically, if someone would give me to write a code and I don't know the advanced level of Verilog, okay, how would I write? I would write one full adder code over here, then again full adder code, then another full adder code, another full adder code. Basically, I would write module, input A0, input B0, input C in, output S, not output C out. Then again, I would write assign S is equal to A0 XOR B0 XOR C in. That way, right? That's how you write a code. But this is increasing the line of code. Let's say here you have 7 lines. Then here also 7, 7, 7, 7 fours are 28 lines of code. So it almost is increasing your line of code. That is why what people came up with is with a concept of called instantiation, okay, where you write just one full adder. The code sum is equal to assign, sum is equal to assign, carry is equal to just once, and then you instantiate that 4 times for all your 4 full adders. That is the concept which we used to write for 4-bit ripple carry adder, okay? And the expression is the same. The block diagram, like one full adder would have the same thing, A XOR B XOR C in. C out is, you can either use AB plus BC plus CA or AB plus C in A XOR B. So can you see the screen? This is what EDA playground is. Are you able to see?
Yes, ma'am.
Yeah, so basically here, this is EDA playground. So new would mean started. This is my playground, okay? That's how they've named it. This is entire thing is my playground. Then run would mean run whatever the code I have written over here. Save is for save. Then here languages and libraries, you need to choose your test bench. That is System Verilog or Verilog you can choose. There are different options over here. VHDL, Specman, Python, C++, Perl and CSH. So as we are coding in Verilog, you can just choose Verilog. UVM you're not using. UVM is for System Verilog, like your verification. So choose it as none. Then no other libraries. Yeah. Tools, there are different tools over here. Aldec, Riveria, Cadence, Siemens, Questa, Synopsys, all these things. You have to choose Siemens Questa, okay? So choose Siemens Questa, then no global options. Then I think this is, it will take it by itself. You don't have to do anything for compile options and run options. Then here, runtime is fine. Then open EP wave after run. EP wave is the output, okay? So you need to tick off this open EP wave after run. That's it. And then you can write your code. First, we would be seeing your design and then we will see the test bench. Now, what did we tell? We are going to write code for this, right? 4-bit ripple carry adder. So first you need to write a normal module for full adder, okay? Normal full adder code. How would you write module? It would start with module, end with end module. Full adder, then input A, input B, then input C in, output sum, output C out. We have for this module, for a full adder, assign sum is equal to XOR B XOR C in, assign C out is equal to A, B, B, C and AC, okay? This completes your full adder code. Now when I say what is instantiation, you are calling out this code 4 times because you have 4 full adders. Okay, you have 4 full adders. So you're calling out this code 4 times. How do we do that? Now I have declared in the same design itself, I'm declaring another module, okay, and an end module. What does this do? This is a ripple carry adder, RCA 4-bit, because you have 4 outputs that is coming, S0, S1, S2 and S3. So yeah, 4-bit. And then here, this is a new method of declaration. This is a, what is this called? Any idea? Within the square brackets, I'm giving A. What is this called? Which form of
Ma'am,
representation?
number of input bits.
Yeah, that is number.
Array.
Yes, so this is an array, right? So I'll just write it over here. Array representation. Correct. So you have input A declared as an array. Then you have input B, which is also declared as an array. 0 is to 3. That means 0, 1, 2, 3. There are 3 in, this is actually a vector form. Array is also correct. This is in vector form. Vector form. Okay. So you call this as a vector form of representation. So 0 to 3 meaning what are the different stages you can have? 0, 1, 2, 3. This is a 4-bit vector. Okay, A is a 4-bit vector. Similarly, B, then Cin is just 1 bit, so you don't have to call it. You can also write it as this way, 1 bit. Okay, but you don't have to declare 1. Only if it is 2, 3, 4, more than 1, you have to declare it. Then output is also given as sum, 4-bit vector output sum, and then C out. Then over here we have internal C. In this, the carry out of 1 is going as C in as 1. This C in and this C in, if you just give it once, that means it will get confused, right? Which C in are you referring to? So this C out is given as C in over here. This C out is given as C in over here. This C out as C in. This is an internal kind of a thing which is going on in 4-bit triple carry adder. It's an internal thing, okay? So for that, you need to declare this as wire. Whatever is internal within a circuit, you just know that your output is S0, output is S0, S1, S2, S3 and 1 carry. That, and this inputs, that is C out to C in, C out to C in, C out to C in is your internal design. For that, you need to declare it in wire. Whatever you're declaring inside a circuit as not the input or output, you need to declare it as wire. So all these are wires, C1, C2, C3, which all, so C1, C2 and C3 are your wires, and finally you have one carry output. Okay, so now these are the internal carry wires. Then this is what I called it as instantiation of 4 full adders. So I am naming all the full, see here I have used the name full underscore adder. I should call out the same name, okay, for full underscore adder. Then I have given 4 different names, FA0, FA1, FA2 and FA3. These are the 4 different names given, and then I declare the input and output. See, over here for first full adder A0 and B0 is my input. Similarly, I have given A0, B0, C in is your, see, C in is the input, and then the output is S0, and the first carry out that goes on is C1. That C1, you see I'm calling here. So what I mean is this C out is seen here, right? Similarly, here in my code, this C1 would be the C in for this block, and then I have some 1, C2, then A1 and B1, A2, B2, A3, B3. This C2, the output of this first full adder, will be the input to my FA2. Similarly, the output C3 of FA2 will be the input of C3. Then I have sum 3 and then C out. Is this clear to you all? Such type of circuits, repeating blocks, that time you need to make use of this kind of a method. Okay, you're declaring it just once and then you're calling it out 4 times with 4 different names. So yeah, that's it. And then let's see how the test bench of this code would work. Yeah, so I told why we are using time scale. This is for the delay and precision. Then yeah, module test bench for RCA 4-bit. I have just put an TB underscore for this. Then I told you inputs you need to declare as registers and output as wires. So I have just declared it as reg3 is 20 A and B, C in register and then wire. And then I'm instantiating. Here also I've used the same names. So RCA, ripple carry added 4-bit, UUT, unit under test, dot AA, dot BB, dot CC that way. And then initial begin, this is for beginning of the waves. And yeah, this in the last time also we had dump file, dump.vcd and dump var 0. This is only for EDA playground, that you need to write these two statements for the EP wave, that is the output wave to come. Okay, this is only for EDA playground. You don't have to follow this everywhere. This is just for running it in this EDA playground. You need to write dump file. Dollar, anywhere you see dollar, it is just for the simulation purpose. So dollar dump file, dump.vcd and dollar dump var 0 is just for EDA playground. Then initial begin, I have given a begin. So I give an end. Then again initial begin, display time and whatever, display monitor is just for dollar time and dollar. All these things are just for someone to understand that your in your simulation you have like time displayed A, B, C in sum and output declared. Okay, you see you need to put this one or mark after time and after all the input declarations, one mark and then the output. It is kind of to differentiate. Okay, time, then all the input combinations over here, and then the output combinations. Then yeah, here also I have represented everything in binary and it is 4. See, last time it was just it depends upon the bit. So here it is a 4-bit, so I'm writing it as 4 percentage 4B. Okay, then the test cases. So I'm giving different test cases over here for A and B, 4-bit input. Similarly, I have given a delay of 10, then finish simulation and then end. Now let us see how the output would look like. So this is your design source code. This is your test bench code. Then I give run over here. So here is your log where all your, if there is any error, see, it displays run all, what are the input output have which you have given. Let me just check. Yeah. So that, and then how much time it has taken, 50 nanosecond, because you have 4 inputs. So 50 into 10, which is 55 into 10, so which is 50 nanosecond, and then there are no errors during QRun, vlog. All this is compilation perspective. There's one warning. Warnings are just for your code to be system clean. Only you need to make sure that you don't have any errors. Then it says finding VCD file, because we have given these two statements, this dump file, dump VCD and dump var 0. So it finds that VCD file and then it has dumped your code in that VCD file, which is basically this output. Okay, and now when it comes here, there's an option get signal. So here whatever signal you want. Okay, so I have A, then append selected. Okay, it will append that. See, A has come in your background. Similarly B, this also I do append selected, then C in. All these are my 3 inputs, then C out, then sum. Yeah, close. Okay, this is first to verify the, then when I do plus, it's a vector. So this is how an actual vector would look like. Yeah, so A 0 1 2 3 for A, 0 1 2 3 for B, then C out is just 1 bit, and then sum is again 0 1 2 3 4-bit input. Now you see here for 0, there's obviously nothing. Yeah, when your A is 0 0 1 1 and your B is 0 1 0 1, your sum would be this and then your C out would be 0. Can we quickly calculate this? See, 1 plus 1 is 0 as the sum and 1 as carry. Then 1 1 0. Similarly 0 and then 1. Then 1 and 1 is 0 and 1. Then 1 0 0 is 1. Perfectly fine. So when I verify also, I'm getting the same output. Similarly here 1 and 1 would be 0 and then it goes out to 1 again. Then 1 1 0 would be 0 and 1. Then 1 1 0 would be 0 and 1. 1 1 would be 0. The sum.
Understanding that.
Yeah, but I'll just write it once for the others. Yeah, let me just explain what I'm doing. So what is let me take this triple one and oh, I'm sorry. Yeah. Triple one zero, was it? Triple one zero? No, just four ones and triple zero. Okay. This and the other input was 0001. Am I right? Yeah, 0001. Okay. So these two are your inputs. Okay. In this case, the third case, this part. Okay. Now I'm doing the addition for it. So your output would be, yeah. How would your output be, guys, now? See, one.
0, ma'am.
Yes, so the sum output I'm telling, so 0, exactly. 1 plus 1 is 0 and carry would be 1. So that carry would go over here, right?
1.
Then again, what is 1 plus 1?
0.
Exactly. So 0 again you would have a carry of 1. Again 1 plus 1 is 0 sum and carry 1. Again 1 plus 1 would be sum 0, carry is 1. So this is with respect to sum, and then we have carry as 1. So similarly here you have sum as 0 and carry as 1. You can see 1 is high and then 0. So have you understood this? So here also you can see vector representation, right? So for 0, 0, 1, it is 0, 0, 0, 1. So here wherever it is 1, it is high, 0, it is low. This is how a vector representation would work. So is this clear to you all? This particular code? Great. Okay. So whenever anyone is asking you to write an instantiation code or explain what is instantiation, it should be very clear to you guys. Okay. I suggest you to practice more codes like this. You can go for a full subtractor, anything. Just four or more than four similar blocks. You just need to define that code once and then call out that code multiple times over here. This is called as instantiation. Okay. So don't forget that. Then I think the test bench is also clear to you how to write the test bench. So I think with this, I will end today's class. I don't want to burden you more.